different polarity of the switching current, that will always switch these two MTJ into the opposite state. So for example, if the left-hand side is the anti-parallel, then the right-hand side will be parallel. And then, if you have another input, we call it the input B, and you have a B and B minus, then you will always choose the left-hand side or right-hand side MTJ to read it. So if we write down something like a truth table here, you will quickly find that this A and B interaction looks like an SOR or XOR. You can change the reference point of your sense amplifier to change the reading, right? So this would be like you are doing a simple mathematics. If you want to do matrix vector multiplication, then you have this kind of device. Then you can put this you can put your vector as a B input, and you have a array stored some information. Then you can easily do this NVM. And this is very useful for the AI application. So here's more details that how we do it. So now we fabricate a array of this kind of device, so that if you have here I show 4 devices, and each of them you have input A to write the NTJ into different states, and then you apply a B signal to read the MTJ, and at the end this current will all accumulate and give you a sum of this all the conductivity multiplied by this V read, so that you get the NVM. And this NVM is a binary, so it's like allow me to show this. It's just like this. You have A and B. If A is 1, B is 1. 1 times 1 is 1, right? So you have this simple mathematics. But this happens in the memory array, which means that you don't need to take all the data outside this memory to the logic and do the computation and send it back again. You can do it in the memory. Okay. And because now we don't have a good shrinkage process yet, but we can put two MTJ, make it far from each other, so that allow us to have a high yield. So we fabricate this in E3. That this black line is the SOT channel, and we put two MTJ on each side. And the middle terminal is on the other side. So in this cross-section, we didn't see it. Okay, and this is the layout of the backend. So here is the device. We have a single SOT channel, put two MTJ on it, and we need the top electrode to connect it out. And this is the overview. But if you are familiar with this front end and back end layout, you might think this right transistor is very big, and this is for the experiment wafer. So we don't optimize the cell size. We just try to make the right transistor as big as possible. If one day we don't have a good we don't have a good SOT, we can still switch this device. Okay, so let's see how it works. So here is one of the example. So as I show, we have a middle terminal for the right current. So I have to always write this MTJ1 and MTJ2 into the opposite state. So for the first point, if MTJ1 is in the AP state, MTJ2 will be in the AP state, and this will just alternatively, because we apply a right current alternatively positive and negative. So that here is the right sequence. Okay, and we also try the high-speed measurement, but this time because the SOT channel is larger, so the RC delay is more significant. So now we cannot go down to the 0.4 nanosecond, but we stop at the 10 nanosecond. Okay, and this I already showed you. So later I will explain why we need a high resistance. So here is one of the examples. It's like we have an SOT, so it doesn't matter how we change this RA value, the right voltage can always keep the roughly 0.4 volt. This is for the DC. But we also have the STT. So for the STT, it's really simple. If you increase RA by 10 times, then you need to increase the right voltage by 10 times. And this is so far impossible for our core voltage for the CMOS wafer. So that's the reason why if you need some high resistant application, SOT is the best choice. Okay, and this is the array should move. So it's show you that we can do it down to the 1 giga frequency, and the right voltage is roughly like 0.2, and from the P2IP and AP2P is roughly 0.1. And the criteria pass is like 100%, no error rate. Yes, please.
Sorry, quickly, what does shmoo mean?
Actually, I don't know what does shmoo mean. So my colleague always show this. Actually, I don't like to show the shmoo plot.
Oh, okay.
This is like for the semiconductor people.
Okay.
So because for example, this kind of plot, we always if you check our paper, I always show the contour, because contour allow you to check the switching probability. Yes, but they need a criteria, so they don't want to show their criteria. It's better that you just cut it here, but probably people don't know how high the error rate we need. So here is because it's only 4K, so we set the criteria, which is 100%, no error, and it's this one. But I don't know whether this is a standard or not for the memory. Yes, please.
In the previous slide, you showed the reading energy is reduced if you increase the resistance. But
yes.
Do you compromise on the reading speed?
That's a good question. So actually, here I talk about is the cumulative current. We are achieving we aiming to achieve some certain value. So that's a good point, because if we increase the RA by like 500 times or 3 orders, then the read speed will become very slow. That's true. So if you use it as a conventional memory, you do not really gain so much benefit in the read energy. That's true. Okay, and then this is the read window, but this is we substrate the peripheral circuit resistance. That makes it look much better. But here, I didn't show the log plot, but even you check the log plot, there is no any device in between. So our device, at least for the 4K, so far it shows a very good read window. You don't need to worry about the read window one. And the one like just X is like we are trying to do this kind of accumulate current. So here we actually we do this not on a real array. It's because our current array design don't allow us to turn on all the transistors. So what we did is like we make a sequence that allow you to randomly switch the MTJ and read the current of each MTJ, and then you get the total current. And here we guess the most challenging one level would be in the center, because you randomly have around 32.1 and 32.0 that give you a high and low current. And even though we check the center point, the overlap is less than 2%. So I think this is a very good demonstration that we can do a multiple level of the cumulative NVM. Okay, so not just the NVM, because we have this array. So one day before I submit the paper, I think that we probably can try some edge detection. So this is what we do. It's like because the edge detection, if we want to find this edge, it must be for the like a 0 in between the 0 and 1, right? If you have the image and you try to find the edge, this edge must be in between the 0 and 1. So we use this array to do the XOR for every bit. So this allows us to here would be an edge. And this is the real result. So the left upper figure is the input. I put a 256 is a grayscale image into the SOT. So we use this image to write this memory. So it looks like a SOT-CIM, no problem. And I also use the simulation, like a Kenny model, to find the edge. So this edge detection looks quite well. So we can map out the SOT-CIM image edge. And then we try it on our device, on our 64 by 64K array. It also looks quite good. But if you look carefully, there is an error bit. This at the middle of this C, it's actually black, but turned out it's a white one. So this is a defect bit in this array. But that's I think for this one, I think that's for us it's good to show because it looks more realistic. Okay. Okay. So at the end, I would like to show this one. This was one of the paper by Professor Yomini. They are working on the CIM, and in this paper, I just get the conclusion. It's like if you want to do the cumulative current, and you want the array size to be larger, then you need to push the resistance, or I would say you need to minimize the conductivity. So in their paper, they show that the ideal case is this one. If you can have a device that the conductivity is lower than 10 to the minus 6, and the variation is also good, then you can have a 512 by 512 array. And in this work, in our work, the RA 10,000 actually located here. We have an even better variation control on this MTJ. So we think this is very close to this ideal case. And we are working with Professor Yomini now, try to demonstrate a real CIM device with the help of the simulation, and we also work on the real device. So now, nowadays, it's ongoing that we are preparing 1 mega SOT-MRAM array with this function. And hopefully I can show you in the near future if everything goes well. Okay. Yeah. So, okay. So the summary, I just leave it here. So actually, today I'm very glad that to be able to show you that SOT is really superior in some aspect. And of course, there are still some solutions. It's ongoing. And we are not, I think for the SOT-MRAM array is at a very early stage. So we are not like compete with everyone here. We actually try to find a teammate that we can work together. So if you have any idea or there's possibly cooperation, we can work together. I think we are very happy to talk more about the details. And at the end, I would like to thank everyone who had a contribution in this work, including my previous boss and the current boss, and all the people in E3 and TSMC, that everyone worked so hard that I had a chance to show you this result. And thank you very much.
So, what is the efficient spin-hole angle or the SOT efficiency of the device?
We actually at the very beginning we fabricate the whole bar structure, and we think it's roughly like 0.5.
0.5 is spin-hole angle or
Yes,
SOT
spin-hole angle. The spin-hole angle. We use the second harmonic measurement. Yes.
And what is the magnet that TSMC used?
Magnet,
paramagnet. That above the doped tungsten.
doped tungsten. Yes. Yes.
Above that, the
Above the doped tungsten is cobalt and bronze.
Okay.
Yes. And the free layer structure is kind of tricky. So it's not like a single layer. You need some engineering. So you can that could also be part of the high, the reason for the high spin point.
Thank you.
Thank you.
So I have a question about the importance of spin hole angle.
Yes.
So I think the large spin hole angle
Beta tungsten is because of, it is resistive
Yes.
than other materials.
Oh yes, yes.
So it does not mean that the spin current is large, but still, is it useful, or you need a large spin hole current instead of a large spin hole angle?
That's a good question. Actually, we at the very beginning we also like most of the people we working on improve the spin hole angle, but at the end we found that spin hole current or the spin hole conductivity is more critical. So nowadays we don't pursue the high spin hole angle anymore. We pursue the high spin hole conductivity that allow you to have, because we also want to reduce the shunting current. If you apply a current in this SOT channel, that you will have some shunting current in the free air. So the conductivity of this SOT material, of course, is higher better. So if you multiply the spin hole angle by the conductivity, that's now the figure of merit that we decide which material is better for the SOT.
Thank you.
Thank you very much.
Professor, I just had a question out of curiosity. Yes, so I wondered that in your SOT devices,
Yes.
what is the order of the interfacial roughness that you aim for? Does it affect the performance? Or?
Yes, yes. The interfacial roughness definitely is a key. So at the very beginning, while we try different SOT material, we also noticed that some of the material have good result in the like a SOT coho, this kind of structure, but does not have good result in the SOT and covalent boron. So if you consider the interfacial, that we think the interface spin transparency could also play a very important role. Yes.
Okay, so here, could you comment on like what is the order you're going for of roughness or say transparency in your devices that you have just presented?
So far, after we really fabricate a device, we don't characterize that anymore.
Okay.
Because we can just use the device performance to decide.
Right.
It's just at the very beginning while we see some conflict, we don't understand it. We do some more deep, careful examination, including checking the TEM and do some study. But nowadays, if we have any idea that we pull in, that we just check the device performance. So it's already been a while. We do not really consider the interfacial.
Okay, so typically like sub-nanometer roughness, like by conventional fabrication techniques, the roughness levels achievable, those are good enough, you would say, or is it?
It's not necessary to be smooth better.
I see.
That's another secret.
Okay.
So you probably don't expect that you have the best result for the smoothest, the most smooth film. Sometimes roughness can give you something unexpected. That's all I can say.
Okay, thank you.
Thank you very much. I have a question, follow-up question about spin hole conductivity.
Yeah.
What is your favorable value for the spin hole conductivity of order? It's also okay. Order of the spin hole conductivity.
This one also is a very like early study. So so far I don't have the numbers in mind, but the data I can share with you. That because I don't have the number here, and then I don't remember it yet. So I probably can if you give me your information or you email me afterward, I can tell you. But like I mentioned, nowadays we don't work so much on the detail, the fundamental characteristic anymore. So every idea we have, we just directly make a single device. That's more straightforward for my boss. So that's also how I do it. Yeah.
So if there are any material with the favorable spin hole conductivity and a good compatibility for manufacturing, you still interested?
Yes, for sure. Yeah.
Thank you.
Still nowadays we're still trying some materials. And those are like, for example, Chi-Feng, their group has a lot of different alloy, including the platinum, chromium, platinum, cobalt, something like that. We're still trying to integrate it into the bus. But platinum for the NTJ, it is not so friendly. So you will suffer from other issues. But I think that's easy to, you can find a reference paper talk about using the platinum as a sealing layer.
Okay, thank you very much.
For the XOR operation, so you showed the comparison with other non-volatile memory.
Yes.
So if you compare the properties with the CMOS, so CMOS also can do the XOR operation.
Yes,
Oh,
yes, that's true.
Is it still better at more advantages?
CMOS is, here we talk about this story is like we think that CMOS you will not, it's like not in memory, so we don't put it here.
Oh.
But what you mentioned is like we need to consider you transfer the data out the memory. And as I know, but I'm not very expert. As I know, this transfer data energy could be 2 orders higher than you do the operation. So that could be another totally good.
Much more efficient.
Yes.
The things I see.
Yeah.
One more question. So in the first part, you showed the switching current and switching energy.
Yes.
Which is more important?
Switching current.
Smaller switching current is better than the smaller switching energy.
Because the figure I showed, I think that's good for the educational purposes. It's like because the figure I showed do not consider the peripheral circuit, and you know that our targeting for the advanced node peripheral resistance is very large. So if you have a small current, that's definitely good for the whole circuit. If you consider all the integration circuit, the small current is the key.
I see. Yes. Thank you.
Not just the SOT itself.
Thank you.
For the MVN operation, a 1T1 array is sufficient to doing this. So I'm wondering the purpose of using the MTJ pair.
Sorry, you say for the MVN
MVN operation.
Yes.
A 1T1 array is sufficient to doing this.
Yes.
So I'm wondering the purpose of using the MTJ pair.
MTJ pair. Oh, you mean if you want to do the MVN, then you can use one transistor to write it, and then use the control the word line.
Yes.
So you treat your write current as one of that, as one of the input, and your write and your word line as another input, right?
Yes.
Okay. So for this one, you can really have store the memory, and also you can have the operation. But if you use only 1T, 1R, as I know, that would be more like a AND function. If you think of, for example, if you have a B negative, you always cannot read the NTJ, so you don't have this SOR. The resistance will always be high. It could be an AP state or just like insulating, right? So the only one possibility you read the low resistance could be if you turn on the word line and also you write the NTJ into the low resistance state. Am I right?
As far as I understand, it's for the logic operation, but for the MV operation,
Yes.
it's just
Oh, you mean to read it out, to read out the MVM?
yeah.
Okay. To read out the MVM, if you don't have this, you need to first map out all the memory. So accordingly, for example, I have a weight matrix. This weight matrix, you need to write all of them one by one. And then you need this to control the reading. But for the x equals to 0, you will not able to read the current because you turn off the transistor. So even though this is the low resistance, what you read will be 0 if this one is 0. So your X input will also always give you 0. Am I right? It's like you cannot do the XOR on the memory. The only thing you can do is like you write every bit, and then you know that this already is the result of the A11X1, so that you can accumulate all the current. That's you need to do the operation somewhere. You already know the result, and you store it in this array. Instead of you can do the logic operation on the array. So the purpose for this device is like we don't need to know the result. We can just put the input into this array and do the computation on it, and the outcome could be the computing result for the NPM. That's the difference in between this structure and the 1T1R.
Any more questions? No? If not, let's thank Dr. Song again. Today's schedule will be a little bit different from yesterday because we're going to have 2 lectures.